Hello, everyone. Can you hear me? And can you see my screen? Yes. Today we are going to try this double windows. And this is because we have circumstance today that we need to, for example, we have reached page 10 and we need to refer back to page 5, some formula or some theorems in page 5. So I think it would be convenient for us to have these two windows at the same time. And as you see, today we are going to talk about Heine's theorem, one of my favorite theorems in analysis, because we are going to say that it is very useful. The theorem itself is very useful, and the proof of the theorem provides us with many useful and classical methods in the subject of analysis. So let's start. Yeah, in the past, we have learned the limit of a sequence, and we spent a lot of lectures dealing with limit of a sequence. Can anybody remember the definition, the epsilon n definition? Yes, we have used it many times. A real sequence an convergent to a real number a. We use epsilon n language to describe this. Is for all positive epsilon, there's a natural number large n. For all small n greater than this large n, the absolute value between an and a less than epsilon. And in the previous lecture, we also introduced the limit of function at the point. That is, similarly, we have a definition in a similar form, right? That is epsilon delta, right? So a real function fx, when x goes to a real point x0, convergent to a, we use epsilon delta. For all positive epsilon, there's a positive delta. For all x, such that if the absolute value between x and x0 less than delta, and also we emphasize this red one, right? We emphasized this last time, x cannot equal to x0. Then we have this, this should be a, sorry about this, fx minus a minus the right side, the absolute value less than epsilon. That's the definition of limit of function at a point, right? Okay, so what does Heine's theorem say? Heine's theorem will tell us that the relation between the limit of a sequence and limit of function. So here it is. So x0, small a, large a are real numbers. F is a real function defined in the neighborhood of x0. Remember, we had a convention that what does it mean by in the neighborhood of x0? That means there exists a delta positive such that I equals to x0 minus delta and x0 plus delta, right? So we had this convention before. That means in the neighborhood of x0. Okay, so we have these real numbers and this function. Then we have this limit holds if and only if for all this sequence xn in this neighborhood of x0 satisfies this, we implies this limit. This is a kind of a complicated structure. Firstly, let us just see an example. We just take fx to be x squared plus 1, and a is 1. This theorem claims that this limit holds if and only if for all these kind of xn goes to 0. Well, we have introduced many sequences goes to 0. For example, this, and there are way many, right? There are many of these kinds of xn. So for all these kind of sequence, we insert this kind of xn into this x position, and we have the same limit. That is an example. Just try to somehow help you to understand this theorem. Okay, next we are going to prove it. And before we start our proof, let us again just try to find the structure of this proposition. We have 3 limits in total: the red one, the purple one, and the blue one. The structure is this. The proposition claims that the red one holds if and only if Q implies R, right? So if we want to prove this theorem, we are going to prove both of these sides. For the necessary side, we need to assume P and also assume Q and try to deduce R. Is that clear? And for the sufficient part, that is the opposite side, we need to assume this bracket Q implies R and finally try to deduce P. Yeah, from this structure, we can see that which side is simple, is simpler. Yeah, the necessary side, right? Oh, we can guess that. So we start our proof with the necessity, okay? Okay, now we need the double screen, double windows to work. Now we just, okay, we just put our theorem here, and so we can see them at the same time, okay? So for the necessary side, as we mentioned, we need to assume the red one and also the purple one. Try to deduce the blue one, right? So we use epsilon delta to write the definition of the red one. We have this, right? Again, this x cannot equal to x0, okay? And also for the purple one, let's write the definition. Okay, remember the definition of a sequence. It starts with for all epsilon which is positive, right? As it is a for all, can we take the epsilon just equals to the delta we obtained from this limit? Of course, yes, right? It's a for all. So we take the epsilon to be the delta. So we write as for previous delta, which is positive, there's also a large number n, and this holds, right? And this epsilon is replaced with delta. Okay, now let's say xn is not x0. This is because the condition, right? and also xn minus x0, the absolute value of xn minus x0 less than delta. So this condition holds. Yes, and according to this proposition, if this condition holds, we have this. So we just substitute f this x position as xn, then we have fxn minus a, the absolute value less than epsilon. Then we can conclude the blue one. Why? Because for all epsilon positive, we have found a natural number, right? For all small n larger than large n, we have this inequality. According to the definition, we have the limit. So yes, the necessary part is easier. Any question? Okay, let's proceed for the sufficient part. For the sufficient part, we need assume that the purple one implies the blue one and try to deduce the red limit, right? So we argue this side by contradiction. According to our logic, if this red limit is not true, then we substitute every for all to there exists, and for all exists to for all, right? For all to exist to for all, and we have this kind of proposition. Notice there's a for all positive delta. Then we take delta to be 1. There exists x1 such that this host implies this host. Also, we can take delta to be 1 to be half. There exists x2 such that this host implies this host, right? And we can proceed this, let delta to be 1nth. There exists xn such that this host implies this host. Okay, now we have obtained a sequence xn such that this host implies this host for all n, right? Because for 1, for 2, for n, and forever. Okay, by sandwich theorem, or we can see squeeze theorem, we have limit n goes to infinity, xn is convergent to this x0, right? Yeah, because apparently this goes to 0. But we have this. What does this mean? This means the red limit, the blue limit cannot hold, right? But remember our condition is for all these kind of sequence, satisfy the purple one implies the blue one. Now we find a sequence satisfy the purple one, but not satisfy the blue one. So it is a contradiction. Is that clear? Okay, so this is the proof. Any questions? If you don't have question, I'm gonna ask you a question, okay? Okay, there's going to be. Now let's firstly just conclude some methods and techniques we applied during our proof. The first one is the embedding method. This is a method named I just gave the name, okay? It's very hard to find this kind of names in some analysis books. I try to conclude some method because these methods concluded today are very, very useful in the future analysis proofs. So it would be nice for us to have a conclusion today. Okay, firstly, what is the embedding method? This is the necessary part of our proof. Let's say we have an outer side limit, right? And an inside limit. We somehow embed the inside limit into the outside limit. By what? By this for previous delta positive. So next time when you say there's a composition of functions or something similar as this, a composition, okay? And there's a condition of a limit for the outside function and the condition of a limit for the inside function. What would you do? You can try to write the outside limit by the definition, and for the inside limit, for the epsilon, use the previous delta. This can help you to somehow embed this inner side limit to the outside limit, right? We are going to say this in the future, okay? Okay, secondly, and yes, as I said, you don't have question, let me ask you question. How can we come up with the idea of using argument of contradiction? This is for the sufficient side, right? We start with argument of contradiction. Why? Yeah, because somehow we mentioned here when the sufficiency side, we need assume this Q implies R and try to deduce P. And according to our logic knowledge, it is very hard for us to use this Q implies R properly, right? Because when you want to apply this Q implies R, you need firstly deduce Q is true, which we don't know. Actually, we don't know. And also the Q implies R is the only condition we can apply for the sufficient part, right? So what should we do? The argument of contradiction. Why? Because the argument of contradiction provides us with an extra condition, right? When we use the argument of contradiction, we suppose or we assume the P is not true, which plays as an extra condition. And it is this condition that helped us to finally find the contradiction, right? We suppose this P is not true and find the sequence. We have to assume P is not true so that we can find this sequence, and this sequence helps us find the contradiction, right? So next time or in the future, when you find yourself in a position that the conditions are ambiguous or something is very hard for you to apply, it could be helpful for you to think if you can use argument of contradiction, right? Okay, this is the second one. And thirdly, the epsilon sequence method. This is simple. This refers to this for all delta which is positive. We know that normally this is a for all epsilon positive, so I use epsilon sequence here, but this is just a name. It means every time when you find for all epsilon positive or for all delta which is positive, and you need a sequence, which is quite normal in analysis. I'll repeat this. There is a for all delta positive or for all epsilon positive, and you need a sequence. You can always try to let this delta or epsilon or something else to be 1 over n or 1 over 2 to the power of n or something, some sequence convergent to 0, and you somehow drag out a sequence. Normally, this is the sequence you want. And you can use this sequence to deduce and to proceed. Is that clear? And any question? Okay, so this is Heine's theorem. This is the lecture for today. And finally, our homework. This will help you to review what you have learned, not only the theorem itself, but also the methods we just talked about today. So, okay, see you next time. Bye-bye.